In my time of day, the question is, in my time of day, what was considered doing bad things? What, oh, twisted? Doing something bad was being twisted? It, oh, twisted is slang for drunk right now. I think that the phrase was, and note that wasn't me, but I think it was said. I believe. Okay, we are going to do a couple more examples, boys and girls. Let's just review really quick. Make sure that you understand this piece. I know we covered this yesterday, but let's get it back in your minds. If I draw a function, we'll call it f of x. I want to know the slope of the line tangent at x is equal to a. And so I plot that point A. What do I call the output? F of A. I also create another point, which I call A plus H. That has an output of. Now I use the slope formula. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. What happens to your a's? They cancel. H is the distance between the 2 points. What are we going to do with that distance? We're going to push it to 0. So that's where we get the limit as h approaches 0. So, and there we have the formal definition of instantaneous rate of change at a given point. Let's try another example. Equation for line tangent at a given function at a given point using definition 1. So this is the first definition. If it refers to that, this is what we want to use. And so in order to find an equation for a line, we need two things. We didn't do this one. What is the point on the line? 2, 11. In order to find slope, I don't use y sub 2 minus y sub 1. I use the limit as h approaches 0 of f of a plus h minus f of a all over h. What is my a value? 2. So my a value is 2. We go to work. The limit. Oh no. The smartboard just got dumb. Let's see if it can get back. Sometimes I write too fast. Yep, still recording. There we go. The limit is h approaches 0 of. What is f of a plus h? So I take that 2, that's my a value, 2 plus h, and I plug it in my function for x. So I have 3 times a plus h quantity squared. Plug the a plus h in. Minus 1. Devin has a question. What's the question about the 2? We'll now do the 2, okay? So f of a plus h. Oh, 2 plus h. Yes. Sorry. Yep. Minus f of a. Yep. 2 squared is 4 times 3 is 12 minus 1 is 11, which is right there. Divided by h. I have the limit as h approaches 0 of oh boy. No. 2 plus h. So So when you take 2 plus h and you FOIL it out, you get your h squared, so 3h squared. Then you get a 4h in the middle, times 3 is 12h. And then you get 4 times 3 is your plus 12. Minus the 12 on the end, divided by h. What happens? You can see that your 12s will cancel. What else? Factor out an h, so that h will go and that will reduce to 1. Don't worry about the 3. You're right, but don't worry about it. So we end up with the limit as h approaches 0 of 3h plus 12. Can I now plug in 0? And what do you get? 12. So the slope of that line is 12. I plug in 0 for the h. 3 times 0 is 0, plus 12 is 12. So I now have my slope. Question. That is the instantaneous rate of change. So just like a line has a slope that's consistent all the time, that's constant, this parabola at that one point, at that one single point, has a slope of 12. Yeah, try to wrap your mind around that. Yes. Okay, you guys, there's a very good question out here. And the question is, where did the 11 come from? Let me give you that answer. First of all, if you plug that 2 in, 2 squared is 4, times 3 is 12, minus 1 is 11. It's the same as that value. That should be the same. The difference is that might not always be given. Okay. Now that I have a slope, and now that I have a point on line, I could go from there. Take out your calculator. As you take out your calculator, if I go into y equals, I'm going to type in my original function, which is 3x squared minus 1. And then next to that, I'm going to type in the equation for the tangent line, which is 12x minus 13. And I'm going to change my viewing window to be a negative 10, positive 10. But then so that I can see it, because it touches tangent to 11, I'm going to go all the way up to 20. So we're going to go negative 10. Actually, so I can see the y-intercept, we'll go negative 20, and we'll go all the way up to 20. I'll make a scale every 10. Well, the y-intercept, you know, is negative 13, right? So I want to go past that. And then the top point where it touches tangent is positive 11, so I go up to positive 20. If I press my graph, you can now confirm that it's correct. So that's one way to do it. So if you want to see if you're actually correct on the test, you need to show all your work, but you could actually graph both. You can see it touches tangent at one spot. So we have solved the first and most fundamental problem of calculus, which is how do you find the slope at a single point? And we've now solved that on a function. Let's try, we've done 2 that are easy. Let's try a couple that are a little bit more difficult. Okay. Now we have a square root piece. This makes it a little bit more difficult. Again, we need to find the slope. We need to find a point on our line. We have a point on our line. Well, I just wrote down the definition from before, so in case you didn't, remember it, this should be committed to memory, okay? This is something we need to remember. So I'm going to set this up. I need to find the slope. The limit as h approaches 0 of, now, what is f? What is my a value? A is 6. So what is f of a plus h? The square root of 6 plus h minus 2, correct? And we're going to subtract off from that what? I'm going to subtract 2. Whatever I get when I plug in 6. 6 minus 2 is 4, square root is 2. It's exactly that value. I divide that by h. Let's write that in a little bit more simplified form. I have the limit as h goes to 0 of square root of 4 plus h minus 2 over h. Now, as you notice from the previous problems, before we can plug 0 in for h, what do we have to make happen? We've got to get rid of that h in the denominator. Now, you can't cancel off these two h's because that'll be, canceling parts and reducing parts, and Nelson would cut your finger off. Yeah, so we can't do that. So therefore, we're left to a different option at this point. Does anybody know what our option is? Conjugate. And right now you're saying to yourself, well, Mr. Gens, back when we were doing limits, you gave us some problems like this. So you were actually thinking about our learning before we got to this point. So we would have the skills necessary. In fact, some of you guys recognize some of these problems from last year in pre-calculus. So now that we multiply this out, I have the limit as h approaches 0 of, when I multiply conjugates, I'm going to have the first part squared will be 4 plus h. What happens to the middles of conjugates? They go away. That's the whole idea. That's why we do it. And then you get negative 2 times positive 2 is, and what do you know is going to happen with the 4s? But here's the mistake that people make. Please look at the denominator. The denominator says h times, and then this whole thing in parentheses. This is what sometimes people make a mistake with. We need to keep this all as one piece being multiplied by h, so that our algebra will work out correctly. So now I have the limit as h approaches 0 of, what happens to the 4s? The 4s will cancel. What happens to the h over h? That leaves you with 1. So you're left with 1 over the square root of 4 plus h plus 2. Some people are dissatisfied with this because they say you still have an h in the denominator. Doesn't matter. When I plug in 0, I don't get 0 in the denominator, which is the whole idea. Can I now plug in, thank you, Pulley, what did you get? 1 over 4 is the slope. For sake of time and for sake of the process, we won't find the entire equation tangent to the this curve because you know the slope, you know how to take care of it from here, right? Okay. It's the same process. We're just working with square root functions here. So first we did polynomials. All polynomials will work out like the first two problems. Now we did a square root function. Square root functions will work out like this. But rational functions, that's a little bit different beast. So let's try that one, and that will probably be about enough for the day. So we'll probably do example 3 tomorrow. Okay. What's that? We'll see. We'll see. Okay. Problem B. All right. So now this is going to be a complex fraction. if you remember from the beginning of this class, we did spend some time reducing complex fractions, didn't we? Because I knew you were going to see them right here, and I want you to be able to deal with them. So let's just use our formal definition of slope, which is going to be an a value of 2. So I have the limit as h approaches 0. I know I've said it many times, but one more time. What am I actually, by setting up this definition, what am I actually solving for? The slope, the instantaneous rate of change, the instantaneous velocity. Instantaneous, 1 point. The magic has happened by limits. We've done it. So I have f of x, or I'm sorry, f of a plus h. What is f of a plus h going to look like in this problem? One over 2 plus h minus 1. Now I have to subtract f of a. So when I plug in 2, I get 1. So it looks like I wrote a bogus problem. So we'll just write that as a 1. There you go. Over what? H. So I said it was tangent at 0.21 It's tangent at 0.21. Okay. So let's go from here. This looks difficult. Let's just rewrite it. I have the limit as h goes to 0 of, it'll be 1 over 1 plus h. Is that correct? All right. Now I can work with that. So I have a complex fraction. Complex fractions when you have a fraction in the numerator, fraction in the denominator. I need to create how many fractions in the numerator? 1. So I currently have a 1, so I need to multiply top and bottom by 1 plus h. So let's do that. 1 plus h. 1 plus h. If I do that, I have a new limit. The limit as h approaches 0 of. I'll have a 1 minus 1, which is 0. And then I'll have a minus. Not everybody caught that. Does everybody see this? I'm just working out the algebra here. 1 minus 1. And then I have a minus h. So 1 minus 1 is 0. And I just left with the minus h, right? Okay. So I have a negative h over, what's in the denominator? 1 plus h over h, and I'll write it as over 1. So I have a fraction in the top, I have a fraction in the bottom. In order to solve, you multiply by the, thank you, Devon. Multiply by the reciprocal, what happens with the h's? What am I left with in the numerator? Negative 1. Limit as h approaches 0 of negative 1 over 1 plus h. Can I now plug in 0? I can. What do you get? Negative 1. Let's go the full process here because I would like to graph this because, you know, I'm a little bit less sure about this problem than the others. So I just want to say for my sake of clarity, I'd like to make sure that we did this right. So I'm going to find the equation for the tangent line, okay? So we have y equals negative 1x plus b. My y value we've discovered is 1, not 1/2. So 1 equals negative 2 plus b. 3 is equal to b. So the equation for my line, y equals negative x plus 3. So I have my original function. I have my tangent line. And again, every once in a while you got to stop and smell the roses. And when I say that, what I'm saying is this. You got to understand how amazing it is what you're doing. If somebody previous to this course would have told you, I want you to find an equation for line tangent to that curve at one spot, you'd have been like, that's so ridiculously impossible. You've done it, and you did it in 5 minutes. And I'm going to teach you how to do it even quicker in 3 weeks. I know you are. So we type it in. We go 1 over parentheses. Be sure to use your parentheses when you're using rational expressions. X minus 1 parentheses. And then I'm also going to have my line, which is negative x plus 3. Delete, delete. And I'm going to zoom in standard mode. So I'm going to zoom 6. And as we see our graph pop up, whoa. Now, A for the day, what could I, are you sure that that's tangent? How could you find more convincing evidence? Zoom in. All right, let's zoom. Let's zoom. What's fun is we're actually doing some theory work here. So, are you sure? So we could do what again? Zoom in. And if we zoom in far enough, what should we see? The same thing. At one point, so we would actually get to a point where they would both look like a line, right? It would look like an identical line. So we could get small enough to where you could see no discrepancy. And that's really kind of the idea. So anyway, that's the magic. Well, it's so cool, and you guys were all able to do it. I mean, you were able to spit it back out today exactly why it works, and we're gonna push h to 0. We're gonna find instantaneous rate of change, and you know how to do it all. So I think it's neat. So there's 6 problems in case you'd like to practice. That will be stuff that will be expected from this homework. Now, if you want to start tomorrow, that's fine. We need to finish up notes. I mean, there's some other small things that we need to glance at. But, oh, look at this. Mr. Earhart is zoomed all the way in. Can't even tell any difference between the two functions. That's what you need. Good job. And he's really smart. Okay, there you go.